Today we're going to talk about resonance in AC circuits. You may have seen resonance in other classes, in particular like mechanical resonance, where you have say a mass hanging from a spring and you pull it down and let it go and it oscillates up and down at some frequency. It turns out AC circuits can do something very, very similar. In fact, there is like a direct kind of one-to-one analogy in the equations that you can read more about on the internet. Okay, so this idea of resonance happens when we have inductors and capacitors in the same circuit. So let's look at one such example. Let's look at a simple RLC series circuit. So a circuit with all three of those components in series. The order of these does not particularly matter, and we're going to keep this in terms of their values R, L, and C. So at a particular frequency, we know enough about this circuit to draw a diagram of the impedance on the complex plane. So R, L, and C, all in series. That means if we know those impedances, we just add them together. So we have ZR, ZL, and ZC all added together in series. So on the complex plane, this looks something like this. We have our resistance on the real axis, that is ZR, and actually I'll just label that as R. We know that this is the real axis and this is the imaginary axis. So we have our resistance like that. We also, we have an inductance and a capacitance. The inductive impedance is in the positive J direction. So maybe we have a inductive impedance that looks like this, and we'll label it with its reactance XL, because that's like, the length of that vector on the diagram. So we've added that to that, and then ZC is in the down direction, an amount XC. And so the total of these three vectors is, something that looks like this. And this is our Z total vector. It, has some resistance part and some reactance part. There's, some of each. Okay, so we definitely know that as we change the values of R, L, and C, we can change the size of these things on that diagram. What you may not have realized is we can do the same thing if we change the frequency, right? So this AC voltage source is operating at some frequency omega, which is, 2 pi times the normal frequency we use, F. And changing omega, it doesn't change the resistor's impedance, but it does change the inductor's impedance and the capacitor's impedance, right? So ZL was equal to J omega L, ZC was equal to minus J times 1 over omega C. So our total resistance then, our total impedance, we can write in terms of these things like this. C total is equal to R plus J times omega L minus 1 over omega C. We could write this in terms of F also if we wanted to and replace our omegas, but we'll stick with these omegas for now. Okay, so each of these, omega L and 1 over omega C, these are XL and XC, right? These are exactly the lengths of these vectors in the vertical direction. And you'll see something funny can happen here. We have these two things subtracted from each other. All the values in here are positive. Omega is always positive. L and C are always positive. So it is possible that this part could be 0 some of the time. Oops, equals question mark equals 0 question mark. I don't know. So under what conditions would this be equal to 0? Well, you can solve omega L equals 1 over omega C. And you get the following. Omega is equal to the square root of 1 over LC, or if we turn that into a frequency, this frequency would be equal to 1 over 2 pi times the square root of 1 over LC. So these are frequencies where something special happens. Our inductor and our capacitor completely cancel out, and on our diagram, we don't have our total impedance at some angle. We have our total impedance simply equal to the resistance, right? Because these other two vectors, one's going up and one's going down, and so they're canceling out and just leaving us with R as Z total. So this is resonance. This is the resonant frequency, and we'll look at why that is or what's going on here. So if we draw a graph of Z as a function of our frequency omega or F, and I guess this is a complex value, so maybe we'll plot the magnitude of Z or something like that. You'll see that as you get close to this resonant frequency, there is a minimum in Z total, right? Whether this is positive or negative, you are increasing the length of this vector Z total on the complex plane. So your graph of Z total versus frequency looks something like this. There is some minimum, and that is exactly this frequency. So we can call these omega naught or F naught. Different books have different names for them, but we'll use the naught just to indicate that there's some special frequency, something happens there. So this axis is the omega axis, and this value here, where that minimum is omega naught. Okay, cool. So why is this important? Well, if we think about what Z is doing, remember, Z is the ratio of the voltage to the current, right? Ohm's law, V equals IZ. That tells us that I is equal to V over Z. So for a particular amount of voltage being applied, if we change the frequency that voltage is oscillating, so say, it's still going between plus 1 volt and minus 1 volt, we're just changing how many times it does that per second, we can draw a graph of the current as a function of the frequency, and it is going to look like the opposite of this, right? Where there's a minimum in Z, there is going to be a maximum in the current. So we're going to have something that looks kind of like this, where this peak occurs at our resonant frequency, omega naught. So physically, this is important, right? This is the biggest response our system can have to an input, right? So we give it some oscillating voltage, and at different frequencies, we get different amounts of current, and the maximum current happens at this special resonant frequency. So that's the first way that this is important. This is analogous to our mechanical resonance, where if you have a mass and a spring, and you jiggle them up and down, if you do it at the right frequency, you can move your hand up and down a little bit and get the mass to bounce up and down a lot, where if you try to jiggle it at a faster or a slower frequency, you do not get that larger resonant response. And AC circuits are going to behave exactly like that. Okay, let's define some more variables that are going to be useful for talking about these circuits. So the equations we're going to write are all going to be for RLC series circuit that looks like this. So I'm going to draw this graph bigger because this is useful as it turns out. Okay, so this point here is our special resonant frequency. We also have, this peak has some width, right? There's some width to this that it turns out is important. This is called the bandwidth, and the way we're going to define it is like this. If this is our max current, this value is I max, there is some point down here somewhere that is equal to I max over the square root of 2. There are 2 points where that is true. So that's like 0.707 times, that's a 71% of the maximum current. So the distance between these in frequency, so that is like from this point in frequency to this point in frequency, this is called the bandwidth. And you've probably heard that term before in some context. This is the bandwidth, and that is some number of radians per second or some number of hertz that our resonant peak is wide. That's the width of our resonant peak. So the equation for our bandwidth, of course, has to do with our R, L, and C values, and it looks like this. There's another equation that we're going to use in a little bit, but so it is the resistance over 2 pi L. So you can see for big values of resistance, we're going to have a big bandwidth. This is going to be a broad peak. For small values of resistance or for big values of L, the bandwidth is going to be small. This is going to be a narrow, very sharp peak. Really sharp peaks or really wide peaks are useful for different things, and we'll talk about we'll talk a little bit about what those are in a second. Okay, one other variable to define is the quality factor, which is related to the bandwidth. So the quality factor tells us the quality of the resonator, or in other words, how good of a resonator it is. So a high quality factor means if you like make the circuit start oscillating and you turn the voltage off, you take away the voltage source, a high quality factor means it's going to continue to oscillate on its own. Eventually that signal is going to go away, but it's going to oscillate on its own for a longer period of time. A small quality factor means it is not going to oscillate for as long on its own, relatively speaking. The quality factor is also directly related to the bandwidth. And in fact, the bandwidth, another equation you can use for the bandwidth is F naught, our resonant frequency, but on the F axis instead of the omega axis, F naught divided by Q. So Q, or rearranging this, Q equals F naught over the bandwidth. So Q is like the ratio of this frequency value to that width. So if you know Q, you could find the bandwidth, or if you know the bandwidth, you could use that to find Q. One last equation, Q is also equal to XL over R, so that's the inductive reactance, that is omega L over R. Oh, and this is at the resonant frequency, so that has to be omega naught, actually. And these equations come in useful at various points, but I want you to understand that there's a relationship between, how wide this is, this thing called the quality factor, the resonant frequency itself, and our actual, values of L, R, and C in the circuit. There's another version of this equation that has XC in it also. It's not it's not important. You can use either one. The other version is in the book as well. Okay, cool. So we've defined bandwidth. So these frequencies, sometimes they have names. Sometimes they're called the shoulder frequencies. Sometimes they're called like omega 1, omega 2, or F1 and F2. We can call those the bandwidth frequencies or something like that. It's we won't really need a name for them, I guess. Okay, great. So let's erase this. So I want to talk a little bit about what's happening in terms of the physics in this situation. So when we have an inductor and a capacitor connected together, and let's say the capacitor starts out charged, right? So there's charge here stored on the capacitor. Now, at this moment, there's a voltage on the inductor, which means the current through the inductor is going to be growing with time. It's going to be increasing. So some amount of time later, our capacitor is going to have less charge on it, but our inductor is going to have a current flowing through it, right? And then it turns out this current causes the capacitor to charge the other way, and it does that until the current dies down to zero and the charge reaches some maximum, and then the whole thing happens in reverse. So the way I think about it, you kind of have this charge sloshing back and forth between the two plates of the capacitor. In our mass and spring analogy, the capacitor is kind of like the spring storing this energy by stretching the charge apart or something like that. And the inductor is the mass. The inductor is giving some inertial mass to our current. So like once it starts going, it's hard to get it to stop going. It keeps going in the other direction past equilibrium. So that's what's going on here. But that's not what I want to talk about. What I want to talk about is energy. So initially, we have energy stored in the capacitor. And the energy in the capacitor is 1/2 CV squared. And, all of that energy then, let me start that sentence over. At this point in time, when all the charge in the capacitor is gone, but we have this maximum amount of current, the energy in the inductor is equal to 1/2 Li squared. So these are just, if you don't remember these from Physics 211, this is the energy stored in any capacitor. This is the energy stored in any inductor. So the energy is going back and forth between these two different forms as your system oscillates. So that's kind of cool. And sometimes you might be asked to find the maximum amount of energy stored in the capacitor or the maximum energy stored in the inductor. Okay. So let's talk about resonance more broadly. So anytime we have an inductor and a capacitor in series in a circuit, so whatever is going on here, we have an inductor and a capacitor and some other stuff connected. We have these two impedances that if these are in series, we're adding them together, right? This is effectively the sum of these, ZL plus ZC. And at some particular frequency, these two are going to cancel out, right? If ZL and ZC are at the resonant frequency, these are equal and opposite. And so at omega naught, Z total equals 0. This can this can change the rest of the circuit in important ways if the impedance of that chunk goes to 0. So anytime you see something like this in a circuit, you can know, well, at resonance, it's going to look like this, but just, with a wire there. There's no resistance to the flow of current at all. Resistance is not quite the right word. No impedance to the flow of current at all. Resistance means something. Okay, so this is series resonance with ZL and ZC in series. I also want to talk about parallel resonance. Basically everything we've learned so far, including the bandwidth equations, there is a version of that for parallel resonance that might be similar, might be a little different. The equations are a little different. The graphs are kind of the same, flipped upside down, you'll see. So let's imagine that we have an inductor and a capacitor in parallel in our circuit. So we have ZC, we have ZL. So let's see what happens when we put these into our equation for these two in parallel, right? So that's ZC, ZL over ZC plus ZL. And we actually don't have to go very far to figure out what's going to happen. Whatever's going on in the numerator here, those two are multiplying together. We're going to get some finite number, right? Whatever's going on, ZC and ZL are some number of ohms, and multiplied together in the top, we'll get some number of ohms. In the denominator here, ZC plus ZL, well, we already know what this does, right? Because this part is coincidentally the same as our series resonance circuit. That is, when we have this special frequency, the resonant frequency, this whole part goes to 0. So if the denominator goes to 0, the impedance of this whole thing, whatever you want to call this, our z equivalent, this doesn't go to 0 at the resonant frequency. This goes to infinity, right? 0 is in the denominator, so this gets really, really big. So anytime you see something like this in a circuit, you say, oh, at the resonant frequency, that is like a really big impedance. It is like current cannot get through there at all in any way. If we look at the graph of z as a function of omega, you know, this z this z, you know, this is the maximum value when this denominator goes to 0. So we end up with a peak in our total impedance at the resonant frequency, which was the opposite of the series circuit, right? We had a dip. If you're wondering why this doesn't blow up to infinity, it's because there could be, I mean, like really blow up to infinity. It's because there also is, or at least could be, some parallel resistance here that would still allow current through, that would still give us, you know, infinity in parallel with some finite resistance is just that finite resistance. So that's putting kind of a maximum limit on how big our equivalent z value can be. And so, you know, for this graph, we could figure out bandwidth and stuff. Also, the current graph, as you could have guessed, is going to be opposite. It's going to be, there's a dip in the current at this particular frequency. So both series resonance and parallel resonance can be very useful for different applications, and we're going to talk about some of these applications soon.